Okay, now already time is over. This is the evening session. This is MSc Mathematics second year, paper 6 functional analysis. Now, then the continue of yesterday class. Now already 2 units completed. The first unit and second unit both are completed here. Now this is the third unit because very important concept in the functional analysis because the entire these 2 units are already we have referred. The first 2 units that is the basic concepts for linear spaces and through some other examples and also normal linear space. What is the norm? Norm of a vector. Yes. And according to the normal linear space, how to define the normal linear space, and also mention the some other examples are also have discussed here. Okay. Now, some other inequalities are also there. Now, then the continue of the part is what is the Banach space, and the examples and also we have explained the properties of Banach space. Now, this is the third unit, bounded linear transformation. Students, listen carefully. Can you hear me?
Yes,
Hello?
sir. Yes, sir.
Oh, okay. Now there is the main problem is today we will discuss the through the mobile because due to the power problem. Is this screen share is there? Sir, is it visible? Third
Visible,
unit
sir.
visible are there?
Yes, sir. Visible.
Okay, thank you.
Visible.
Thank you. Now, this is the third unit, bounded linear transformation. Already, we know that in the under UG level or PG first year algebraic concept, what is the linear transformation? Now, here any linear transformation, it is defined that is also it is also read as linear mapping or linear functional or linear transformation. And how to define the linear transformation? Because here T maps R to R or T maps either one dimension or two dimension or three dimension, whatever it is. Up to nth dimension is also defined through the functional part. Now here the linear transformation is defined. Just you have to screen here. Now this is the definition. Okay, this is the recall of the concept of linear transformation in the under user level, and the previous units are also there. Now let L and L dash be two linear spaces over the same scalar field, cap F. Okay, then a mapping. Now any two linear mappings here, L and L dash, there are two linear maps. Now then the corrective map is capital T. Now transformation is denoted by capital T. Now transformation means that is the functional mapping is there. Now here T maps L to L dash is called a linear transformation from L into L dash. Now here T is the mapping. Now that is connected from the L linear space into L dash linear space. It satisfies the following conditions. Okay. Now according to the two-step test, already we have discussed the subspace condition. Now that subspace, the two-step test connect the mapping is linear functional part. T of x plus y equal to transformation of x plus T of y. Here T is the transformation of this part. Okay. Transformation means, students listen carefully. Transformation means that is the functional part. Now linear transformation is T maps T of x plus y Hello. Hello. Please stay on the line.
Good evening, sir.
Very good evening. Very good evening. Some other also joined here. Okay. Please stay on the line. Please stay on the line. Okay. Please see here. Oh, students, see this one. Now, this is linear transformation definition. Now, T maps L to L dash. Be any one of the linear mapping is said to be a linear transformation. Linear mapping or linear transformation. This is okay. Let L and L dash be any two linear spaces over the same scalar field capital F. See the definition, that is 3.3. Definition is there. Define linear transformation means, first of all, you have to take in the T maps L to L dash be any linear mapping, and L to L and L dash be any two linear spaces, and over the same scalar field capital F, as the following conditions are satisfied. Now that is already we have discussed the subspace condition is there. That there are two-step test and one-step test. But same subspaces test must be involved in the transformation part. That is T of x plus y equal to T of x plus T of y. Here, x and y, there are two elements given in the linear space. And second condition is that is the scalar multiplication, that is under the transformation part, T of alpha x equals to alpha into T of x. For all, here x belongs to L, x being any one of the linear space element and alpha be the field element. And that is the one of the definition of linear transformation. And same one step test transformation is transformation of alpha x plus beta y equal to, here alpha and beta are both are scalars and x and y be the linear space elements. Now there are two scalar multiplications, one is alpha x and another one is beta y, and in between the vector addition is closed for transformation for T of alpha x plus beta y equals to alpha into T of x plus beta into T of y. Here x and y both are linear space elements and alpha beta both are field of the elements. Students, listen carefully. Yeah, any field of the elements, here F be the field. That field of the elements is either real numbers or complex numbers. Now all the field of the elements are scalars. That scalar elements must be represented as either real numbers or complex numbers. Now a linear transformation from a linear space or vector space L into another linear or vector space L dash. That is called what is that? A vector space homomorphism of L into L dash. Suppose in examination is given, define linear transformation, okay, or vector space homomorphism or linear homomorphism. Okay, now the definition is same. That the definition is there are one is the two-step test for transformation, and the second one is the direct condition T of alpha x plus beta y equal to alpha into T of x plus beta into T of y. So that is the definition. Okay. Now please stay on the line, students. Already power is here and visible is clear. Okay. Please wait. Students, please stay on the line. Please stay on the line. Power is here. Just see this lemma 3.3.1. Just you have to see and refer is there and connect the system. Please wait. Wait for 2 minutes. Okay. Please. Okay, very nice.
Hello, sir.
Hello.
Hello.
Please
Please
stay
stay
on
on
the
the
line.
line.
Connect
Connect
to
to
connected
connect
to
the system.
hello.
Hello.
Hello, sir. My name చెప్తారా సార్? Can I do?
Srinivas sir. Srinivas sir.
Okay, sir. Thank you.
Okay.
Hello. Students, listen this one. Already you have to define the linear transformation definition. Just to see the screen share is there. Hello. Hello. Can you hear me?
Yes, sir.
See this one. Now, this is the definition of linear transformation, that is T of x plus y equals to, okay, T of x plus T of y. Now here, okay, this one, T of x plus y equal to T of x plus T of y. For here, x and y both are two elements given in the linear space. And second one is the T of alpha x equals to alpha into T of x. Students, listen carefully here. Now, this is one of the important definition of linear transformation for two-step test. And the direct condition is T of alpha x plus T of alpha x plus beta y equals to alpha into T of x plus beta into T of phi. For all here x and y, there are two elements given in the linear space, and alpha and beta, there are two elements given in the, that is the scalar elements. At the same time, that is the field elements are there. All the field of the elements are real numbers or complex numbers. Okay. Now, please change the line. Zoom is there. Zoom is not connected here. Okay. Now here one of the property of for linear transformation, that is see this lemma 3.3.1. Students, is this are you hear me? Can you hear me? Students, can you hear me?
Yes, sir.
Please respond here. Can you hear me?
Yes, sir.
Hello?
Yes, sir. Hearing.
Hello? Students, can you hear me?
Yes, sir. Hearing.
Okay. Now this is the 3.3.1 lemma is there. Now that is T of 0 equals to 0, and second one T of minus x equals to minus T of x. For all here x being the linear space elements. Now 0 space of the transformation is also 0. Okay. Here 0 being the linear space element, then the transformation of the element is the image of 0 is 0. Because T of 0 equal to 0, this is the first property of linear transformation. And second one, here this lemma, see this lemma, T of minus x equals to minus T of x. Because this is the inverse of image equal to image of an inverse. This is the image. Image of an inverse mapping equals to inverse of the image is there. Image is denoted by T of x. Okay. At the same time, just you have to see here. Okay. Now, first of all, we are taking the linear space. We know this property. We know that 0 into x equal to 0 for all. Here, x being the linear element. So, we have T of 0 equals to T of 0 into x. Now, 0 can also be written as 0 into x for linear through the linear space of this part. 0 can also be written as 0 into x is there. Now, again, that value is 0. Transformation of the result is T of xy equal to T of x into T of y is there. Now, that is 0 into, because 0 be the scalar element, because 0 into T of x, because enter that value is also 0. Because already we have proved that T of 0 equals to 0 is there. Again, second condition, T of minus x equals to T of minus x also can also be written as minus 1 into x. Okay, minus 1 into x is there. Now that is minus 1 into T of x is there. Again, that value minus T of x for all x being the linear space element. Now, this is the property of, this is one of the lemma of linear transformation. Okay. Now, second one lemma, this is the first 3.3.1 lemma is there for linear transformation. Okay. Here the second condition is some other examples for linear transformation. Is it linear transformation? That is simply notated as LT, linear transformation or linear mapping, that is denoted by, students, is this okay? Can you hear me?
Yes,
Please
sir.
respond. Can you hear me? Okay. Now, this is the 3.3.2, another one. There are some other examples on the second two-dimensional of this part. Suppose we are to take in the linear space equal to R square, be the real linear space, then the mapping T maps R square to R square, defined by T of x1, x2 equal to, and here this is the condition. Transformation of x1, x2, because here x1 and x2, there are two elements given in the linear space. That result is x2 and x1 is given. Is it linear transformation or not? But here already we must prove that given the condition, we must prove that it is a linear transformation. How to define the, according to this condition, how to prove the linear transformation? Suppose this value is x. So x equal to x1, x2. And again, we have to take in the another linear space element y is there. And in the same manner, y equals to y1, y2. There are two elements. In the linear space x and y. Okay, here alpha be any one of the real number according to the condition of linear transformation t of x plus y equal to t of replacing x by x1, x2 ordered pair, and y be the ordered pair is y1 and y2 is there. Next one is this can also be written as t of x1 and y1 plus t of x1 plus y1 plus comma t of x2 plus y2 is there. Now this is it can also be written as both first coordinates are adding x1 plus y1 and x2 plus y2. Now we are getting the final part is according to the condition for the given the example is t of x1. Say we are to take in the this value is x1 is there and this value is the x2 is there. So t of x1 plus x1 and x2 equal to x2 x1 is there. So here the x2 is x2 plus y2 and x1 is x1 plus y1 by the definition of t under the example. Okay. Now according to this condition, how to write this one? x2 and x1 plus y2 and y1 is there. So x2 and x1, that value is by the definition t of x, and according to the definition, this value is also in terms of y, that value is t of y. So already we have proved that t of x plus y equal to t of x plus t of y. Hello? Some students are also disturbed here. Hello? Please mute is there. Hello? Sir, kindly cooperate with us. Next one. Second condition is transformation of alpha x equals to transformation of alpha of here the replacing x by x1 and x2. That is, again, this can also be written as t of alpha x1 and t of alpha x2. Again, this value is x1, this value is x2. By definition, substituting here t of x1 and x2 equal to x2 and x1. Here x2 is alpha x2 and x1 is alpha x1 by definition of t. Okay. Again, this can also be written as alpha is common under this value alpha of x2 and x1. Again, x2 and x1 by definition that value is t of x. Now we have to prove that t of alpha x equal to alpha into t of x. Now when the both conditions are satisfied, one is the t of x plus y equal to t of x plus t of y, and second one is t of alpha x equal to alpha into t of x. Through the two-step test, we have to prove that t is a linear transformation of r square. R square means that value L is r square means that is the two-dimensional part. Now there are two coordinates here, x1 and x2. That is the two coordinates. Again, x1, x2, x3 is there. All L equals to r cube is there. Okay, that is the three-dimensional part. And up to r power n, x1, x2, so on, xn. Okay, that is t of x1, x2, so on, xn. So given the linear space is r power n, that is the n tuples of the real system. Okay. Now that is the simple example for linear transformation. This problem is also repeated number of times. See this example up to n dimensional part. L equal to r power n already just recently explained here. Suppose L equal to r power n, here n is always greater than 1. Okay. Now again L dash image of the linear space is r power n minus 1. So given the mapping is it varies from r power n to r power n. One of the linear mapping. Now that transformation of the domain part is n-dimensional part. We are taking the x1, x2, so on, xn and the codomain. So that is the image of the part is r power n minus 1. So that elements are also denoted by x1, so on, xn minus 1. So here we must observe here. Students, listen carefully and see this example. We have to take in the n-dimensional of the elements through the transformation t of x1, x2, so on, xn. That equals to r power n minus 1 means x1, x2, so on, x power n minus 1, xn minus 1. So by this definition, it is a linear transformation from L into L dash. Now similarly, put x equal to x1, x2, so on, xn. And again, y be the another element. So that element is also in the n-dimensional part. So y equal to, comparing it with y1, y2, so on, yn. So both elements are linear spaces, linear space in the domain of the part T of x plus y equal to transformation of replacing x by x1 so on xn and y by y1 so on yn. So adding with this condition T of x1 plus y1, x2 plus y2 so on xn plus yn is there. Okay. Now this is by the definition, enter this value is x1, x2 so on xn minus 1. So this value is also x1 plus y1, x2 plus y2, so on xn minus 1 plus yn minus 1 by this definition. So this value is x1, this value is x2, this value is xn. So replacing of the under the transformation by defined part, that value is image of the part is x1 so on xn minus 1. That is the image of the value. So according to this one, x1 plus y1, x2 plus y2, so on xn minus 1 plus yn minus 1 by definition of transformation T. Again, this value can also be written as x1, please note down x1, comma x2, comma so on xn minus 1 plus y1, comma y2, so on yn minus 1 by definition of vector addition in r power n minus 1. So this value is an equivalent to, by the definition, T of x, T of x, this value is an equivalent to T of y. So already here proved that, T of x plus y equal to T of x plus T of y by definition of T. Similarly, we must prove that transformation of alpha x equal to transformation of alpha of, here replacing x by students. Are you observed here? What is the x? Students? Hello? Hello? Please respond here. What is the x? Hello? Anybody respond? Hello? Here, what is the x? X by, we are taking the value is x by definition x1, x2, so on, xn. So this is T of alpha x1, T of alpha x2, and so on, alpha xn minus 1. So this value is x1, x2, so on, xn. So by definition, this value is an equivalent to the image of the part x1, x2, so on, xn minus 1. Okay. Hello. Can you hear me? So this is alpha is common, alpha of x1, x2, so on, xn minus 1 by scalar multiplication in r power n minus 1. So this value is alpha into, enter that value is an equivalent to T of x by definition of T is there. Now T is a linear transformation from r power n into r power n minus 1. Okay. Now this is one of the example for linear transformation. Similarly, some other problems are also practiced here. Now there is the short answer question. See this example and see this short answer question, and to verify the end of this unit, your solution. Okay. T of x1, x2 is given. There are two, in the domain of the values there are two. So that is one of the map is r square. And image of the part is x1 and 0. This is also two coordinates are there. So codomain is also r square. So given that map is T varies from r square to r square, and by the definition T of x1, x2 equal to x1 and 0, we must prove that here the mapping is T maps r square to r square is a linear transformation or not. Okay, linear transformation or not means by see this the above examples, T of x plus y equal to T of x plus T of y, T of alpha x equals to alpha into T of x. Just to see, we have to take in the here one of the values is x1 and x2 and y is y1, y2. So T of x plus y equal to T of x1, x2 plus y1 plus y1 and y2. So T of x1, y1, T of x1, x2 plus T of y1, y2. So that value is x1, x2 is x, y1, y2 is y. So we again T of x plus y equal to T of x plus T of y. Because here the condition is x1, comma 0. So here x1, comma 0 and y1, comma 0 is there. So x1, comma 0 means T of x1, x2, that is T of x. y1, comma 0 means T of y1, y2. So that value is T of y. So T of x plus y equal to T of x plus T of y. Just we have to refer. See this end of this unit. So answer is given. SAQ, short answer question. To verify the end of this unit, there are solutions are also there. Okay. And by see this above examples, according to this, Now we can prove that t of x plus y equal to t of x plus t of y, and second one alpha into t of alpha x equal to alpha into t of x. So this value is x is there. T of alpha of x1 x2. Okay. Again alpha into t of x1 x2 means x1 0. So alpha of x1 and 0, that value is alpha of t of x1 and x2. So that is t of x. Okay. That is alpha into t of x. Similarly, we must prove that second example and third examples are also, see this one. Now that is the practice purpose. Okay. Now here the second condition, t of x1 x2 equal to alpha x1 and alpha x2. Okay. Same that matter. Say this value is x and another y value is y1, y2. So that is the x and y, both are elements are in L is there. Alpha x1 and alpha x2, alpha 1, alpha y2. There are two ordered pairs in L dash is there. Okay. This is also R square. It varies from R square. And again, this is also same. This is the second example. Suppose in examination is a final examination given any one of the defined map is there. We must show that given the definition, prove that T is a linear transformation. It varies from R square to R square. So any one is there or any two is there. Okay. So that's enough. Students, listen carefully. This is the system of M simultaneous linear equation. System of M simultaneous linear equation. M simultaneous linear equation means up to given the M values representation in N unknowns of the form. Now this is the matrix representation. This is also referred in the matrix representation. Okay. 2 by 2 matrix or 3 by 3 matrix up to here M by N matrix is also there. Okay. But here, especially given the linear equations, M simultaneous linear equations in N unknowns of the form. That is A11x1, A12x2, so on, A1nxn equal to B1. Now, here A11, A12, so on, A1n, A21, A22, so on, A2n, and up to AM1, AM2, so on, AMN. This is the MN type of form. Okay. Now, this is the coefficient of this part. A11, A12, A12, A1n, A21, A22, A2n, and AM1, AM2, AMN. These are all coefficient of the matrix capital A. That is the denotation of capital A is there. Now, what is the constant matrix? B1, B2, so on, Bn. Now, that is the variable matrix are x1, x2, so on, xm is there. Now, this is the variables. Okay. Now, according to this one, this is the simultaneous M simultaneous linear equations in N unknown form. Now, that is the representation of x1, x2, so on, xn. So, that value is x. Now, this is the defined varies from here TB any one of the mapping. It varies from R power n into R power m. Now, this simultaneous linear equation of the form converting into the linear functional or linear transformation n type of part. It is the n domain values in R power n. So, m domain values in image of the part, that is R power m. So, T maps R power n into R power m is there. Okay, that's enough. Now, we are taking the value n consisting of the values in terms of x. Say that value is x. Now, this is also belongs to n tuples of the real system. That is the domain of the part. Now, this is also converting into the transformation T of Tx equal to B is there. Now, enter this form is Tx equal to B. B means B1, B2, so on, Bm. That is also belongs to R power m. So, this is the image of the expression. M consisting of the variables, say that is simply notated as B. That is also image of the representation in R power m. So, again, that map is T maps R power n to R power m is defined by Tx equals to B is there. Okay. Now, this is the defined system. Okay. Now, see this, it can prove that easily T is a linear transformation of R power n into R power m. Okay. Now, already we have proved the above example is there. 8.3.3. Okay. In the same manner, through this expression Tx equals to B. See this one. This is the differential part for linear transformation. What is the differential operator? Is a linear. The differential operator is also a linear transformation. Now, this is also in examination. Define linear transformation. Prove that differential operator and integral operator is also a linear transformation. That is the continuous defined part. 3.3.5. See this statement. Let L be the real linear space of all polynomials with real coefficients defined on the interval. What is the interval of this part? Now, that is consisting of closed interval 0, 1. The mapping T defined by, what is the definition of the part? T of P equal to dP by dx. Now here the d by dx is called the differential operator. So by the definition of transformation, this is the differential part of this part. Now differential, it is consisting involving in terms of P is there. So d by P is also with respect to on the differentiation with respect to x. So T of P equal to dP by dx, that is the definition of this part. Now, differential operator is also a linear transformation. So, P of x is also one of the linear operator. What is the P of x? P of x means that is the one of the polynomial in a linear space. dP by dx is above a polynomial and hence it is an element of linear space. At the same time, Q is also there. Q of x is also belongs to L. There are two elements, P of x and Q of x. Simply, it is notated in P and Q, in terms of P and Q. P is nothing but P of x, Q is also nothing but Q of x. Now, P of x and Q of x, both elements are in L is there. Now, that is the domain of this part. T of P plus Q equal to, by definition of d by dx. What is the definition? Definition is, see this one. Okay, what is the definition? T of P equal to dP by dx. But through this one, d by dx of replacing P by P plus Q. So that is d by dx of P plus Q. Now again, that is the differential involving the vector addition. Now that is the dP by dx plus dQ by dx. By definition of this part, dP by dx equal to T of P, dQ by dx equal to T of Q. That is the simple proof. Now again, that is one is the linear space polynomial. Now that is T of alpha of P equal to, through this polynomial, according to the polynomial involving the differential part, no, so that is differential operator is also a linear transformation. That is the second condition is T of alpha P equals to d by dx of alpha P. So that is alpha into dP by dx. Again, alpha into dP by dx is T of P is there. So T is a linear transformation from L onto itself. L into itself is there because L into L is there. Okay. Now, differential operator is also a linear transformation. So that see this example 3.3.5. Again 3.3.6. In the same manner, integral transformation, integral part is also a linear transformation. So in examination, final examination is given, define linear transformation, T maps L into L and L into R is there, or then we prove that differential part and integral part both are linear transformation. So we have to prove that 3.3.5 and 3.3.6, that is then the same proofs are involved with respect to given this question. Okay. Now, what is the defined part? T of F equal to F be the one of the real linear space mapping. That is the L be the real linear space of all continuous real valued functions defined on the element. That is the what is that? Closed interval 0, 1. So integral 0 to 1 f of x dx through the definition part is capital T. So involving in terms of function is also involving in the linear functional part. T of f equal to integral 0 to 1 f of x dx. Here f be the linear functional. Okay, linear functional means that is the linear transformation of L into R. Okay. Now by the definition T of f plus g equal to integral 0 to 1 f plus g of x dx. So that can also be written as integral 0 to 1 f of x dx plus integral 0 to 1 g of x dx. So that the values replacing. So this value is T of f plus T of g. So that is also proved. T of alpha f, that is alpha into integral 0 to 1 f of x dx. T of f means. So alpha into, so this value is an equivalent to T of f is there. So simply that can also be written as alpha T is there. Okay. So again, integral transformation, integral map is also, therefore integral part is also linear transformation. Okay. Now show that T is a linear transformation. This is the defined part and prove that it is a linear transformation. Already just explained here. According T of f plus g, T of alpha f. Simply that is also through the definition. We must prove that T of f plus g equal to T of f plus T of g. T of alpha equal to alpha into T of f. That is the short answer question 2 is there. Now, students observed clearly here. Let T be the linear mapping from a linear space L into another linear space L dash. So T varies from L into L dash defined by T of x equal to 0. T is a linear transformation from L into L dash. This transformation is called zero transformation. What is the zero transformation? T of x equal to 0 for x being the linear element. So that is called zero transformation. So zero transformation is also a linear transformation because T of, again, two values are there, T of x and T of y. T of x plus y is also 0. So 0 can also be written as 0 plus 0. So that is T of x plus T of y. And again, T of alpha x equal to alpha into T of x. Okay, T of x is 0. So that is alpha into T of x. So this proof is also mentioned here through the definition of T of x plus y equal to T of x plus T of y. T of alpha x equal to 0, replacing x by alpha x. So that is the second condition for linear transformation. That is 0 can also be written as alpha into 0. Again, that is alpha into 0 means by definition of part T of x is there. So that is this is called zero transformation. It varies from L into L dash. Students, this is the identity part. What is the identity? So same map is also repeated. I varies from L onto L part. So here same map, same linear space, it varies from onto L part is there. I defined the one of the linear functional or linear mapping. It is defined from L into L is there. L onto L is there. So replacing one of the value here, x belongs to L, I of x equal to x. Here x being the linear space element. So identity map is also a linear transformation. Similarly, I of y equal to y is there. I of x plus y equal to x plus y. So x means I of x, y means I of y. So that is also, we have to prove that I of x plus y equal to I of x plus I of y. I of alpha x equal to alpha into I of x. So that is also one of the proof is there. So identity zero transformation, zero map and identity map both are linear transformation. That is the 3.3.7, 3.3.8. That is a simple proof. Image of an inverse map equals to inverse of the image. That is T of minus x equal to or minus T of x equal to minus of T of x. This is the inverse of the image. This is image of an inverse. T of minus T of x equal to minus T of x. Okay. Now, this is the defined part. T maps L into another linear space L dash is there. Then the mapping T defined by minus T of x equal to minus T of x. Okay. And we have to take in the another one. This is also a negative transformation is also a linear transformation. This is the negative transformation. So this is also a negative map. Negative defined linear functional is also a linear transformation. Minus T of x plus y equal to minus T of x plus y. That is minus T of x plus minus T of y is there. Okay. And again, minus T of alpha x equal to, by the definition, minus T of alpha x. Now we have to converting into the alpha is also getting it outside. Minus alpha into T of x. Okay. That is alpha of minus 1 of Tx. Alpha of minus T of x. This value is an equivalent to minus T of x. We have finally minus T of alpha x equal to alpha into minus T of x. So when the both conditions are verified for in the linear transformation, so by replacing T by minus T, now we can prove that, we must prove that here already we have proved that negative transformation is also a linear transformation. So students, listen carefully. Now this is the different of linear spaces. Now we are applying. We must applying on the linear mapping or linear functional on the different linear spaces region, that is T defined from L into L dash. Now we are already, there are some other properties we have to prove here. Okay. Students, listen carefully. Can you hear me? Please respond.
Yes, sir.
Okay. Are you understand here?
Understand, sir.
Okay. Now, this is also one of the different transformation. Now, still, we are taking the different transformation, that is T1 and T2. There are two transformation connecting with one of the variable is there. Here L and L dash be two linear spaces over the same scalar field. Okay. The set of all linear transformation, it is varies from L into L dash is there. So that is the operations are also defined with respect to the operations are defined T1 plus T2 of x equal to T1 of x plus T2 of x. And again, alpha T1 of x equal to alpha into T1 of x. Here T1 and T2 both are linear transformations and alpha be the field element. So this is also one of the according to the operations here vector addition, scalar multiplication are applying on linear different transformations are there. So on transformations, different or various transformation we have to take in with respect along with the variable. So that is x be the linear space element with respect to x. T1 plus T2 of x equal to, now that is also closed on linear transformation of this part. Vector addition is also closed on linear transformation. Scalar multiplication is also closed on linear transformation. So that is the definition. Now that is the one of the direct condition. Already alpha x plus beta y, this is the subspace condition. This subspace, the one step test of the subspace is alpha x plus beta y. Now this is also connecting with the transformation T of alpha x plus beta y equals to alpha into T of x plus beta into T of y. So T1 plus T2 of alpha x plus beta y, that is T1 of alpha x plus beta y plus T2 of alpha x plus beta y. So this can also be written as alpha into T1 of x plus beta into T1 of y. Again plus alpha into T2 of x plus beta into T2 of y. All scalar elements converting into the outside of this part. Okay. Here alpha and beta are the field of the elements. Both are field elements. And now that is also we are going at outside of this part. Okay. Now taking the outside of this part, alpha into T1 of x plus beta into T1 of y. So alpha is common in terms of T1 of x and T2 of x, and beta is also common. Now that is also connecting with the T1 of y and T2 of y. Now this can also be written as T1 plus T2 of x. This can also be written as T1 plus T2 of y. So that is also derived here. Replacing T1 plus T2 by T is there. We are finally alpha into T of x plus beta into T of y. Now that is also direct condition is also satisfied. So that's why T1 plus T2 is a linear transformation. So this question is also given in the final examination. Transformation, define that various transformation is also a linear transformation. Okay. Under the vector addition, under the scalar multiplication. Scalar multiplication, just you have to see and refer here. Alpha T1 is also a linear transformation. How to prove? Here x and y both are linear space elements, and here beta and gamma both are field elements are there. So we have to take in here alpha T1 of beta x plus, because one scalar is also common part along with the transformation. Alpha T1 of beta x plus, now this is gamma y. This is gamma, not r. Gamma is also there. Now this is the gamma. Instead of gamma, now r is given. So the r is not here. This is the gamma is also field element. So beta x plus gamma y is also connecting with the scalar multiplication alpha T1. So this is alpha of T1 of beta x plus gamma y. So beta into alpha T1 of x, gamma into alpha T1 of y. Okay. Now that can also be written as alpha T1 of x means alpha T1 of x. Now this is alpha T1 of y is there. So scalar multiplication is also verified on linear transformation. So different transformations is also a linear transformation. So again, this is also a linear space because L1 to L8, all the properties in the first unit, all the properties also verified. Different transformation is also here. That is T plus 0 cap equals to T. 0 cap instead of, that is the image of the 0 element. 0 cap means this is the image of the 0 element. T plus 0 cap equal to T for every linear transformation. So T plus 0 cap of x equal to T of x plus 0 cap of x. 0 cap of x is also 0 because that is the 0 transformation. That is, this value is an equivalent to T of x. That is the L1. L2 property is there. That is the inverse, additive inverse is there. Okay, according to the transformation, T plus minus T of x equal to T of x plus minus T of x. This is T of x, and again plus of minus is minus T of x is there. Again that value is 0. because a plus of minus a equal to 0 is there. And on transformation t plus of minus t equal to 0 means a 0 cap of x. Now that is also we can verify the remaining parts are also there. L2, this is also t plus of minus 2 equal minus t, because transformation means that is the image of the element is 0 element, 0 cap. So L2 holds good.
సార్ స్మాల్ డౌట్
Tell me.
ఈ మధ్యలో మ్యాటర్ ఉంది చూడండి సార్, అది ఖచ్చితంగా రాయాలా ఎగ్జామ్ లో? ఓన్లీ స్టెప్స్ వేస్తే చాలా?
ఏదమ్మా
ఈ మ్యాటర్ ఉన్నది చూడండి సార్, ఆ మ్యాటర్ అంతా
no, that is not necessary here. That is our understand purpose. Okay.
ఓన్లీ స్టెప్స్ వేస్తే చాలు కదా సార్ ఎగ్జామ్ కి?
Only steps are there. Okay. There is no problem.
థ్యాంక్ యూ సార్.
Okay, okay, it's all right. Now remaining odds are also there. L3, L4, L5, L6, L7, L8. All the properties are also involved through the different transformation T1 plus T2 of x equal to T1 of x plus T2 of x, and alpha T1 of x equal to alpha into T1 of x. This is also a linear space. So different transformation must satisfy all the axioms, all the conditions L1 to L8. So finally, that is the linear space, and at the same time, normal linear space condition are also verified. So okay, students, this is the end of this part, and see the another exams. What is that? L6 and L8. This is the for understanding purpose. See the short answer question by the above example. Okay. End of this unit, just see and verify your answer. End of this unit, that is the SAQ4. So students, here, this is the main part beginning of functional analysis. Okay. What is the bounded linear transformation? Up to, we have to discuss what is the linear mapping, linear functional, or linear functional or linear transformation. At the same time, how to define the boundedness. Please stay on the line. Please see this example, see this definition. Just please 1 minute more. Please wait 1 minute. Okay. Students, this is the boundedness. This is the main part of functional analysis. This is one of the heart of functional analysis is there. Number of theorems completely depends upon the entire the linear mapping or normal linear space definition, Banach space definition, linear transformation properties, and at the same time, entire all the concepts must be involved in the boundedness of the LT. LT means linear transformation or linear functional. What is the bounded linear functional? What is the bounded linear transformation? Here, T be any one of the linear map. Students, entire this theory is also must and should be present in your final examination. Direct condition is not there, because here this is the definition. Okay, here n and n dash both are normal linear spaces over the same scalar field capital F. Now that is the linear map is connecting with the T varies from n to n dash. Be any one of the linear transformation is said to be bounded. What is the meaning of bounded? Okay. Now this is the basic definition for boundedness. Students, listen carefully. Okay. Now undergraduation level, that is the real number system. What is the complete ordered field? What is the RNS? A complete ordered field is called real number system. Okay. Now complete means completeness exam. Ordered means order exam. F means field exam. When these the three exams are called, that is called complete ordered field. So that is called the real number system. Suppose in the basic representation, what is the meaning of boundedness? Okay. Any subset element is there, field element is there. We must present the in between the any order relation, subset element and field element is there. Suppose you have to take in the one of the real line is there. Real line means a line is consisting of 2 points. One is the initial point and another one is terminal point. Okay. So that is the we have to take in the field of the elements is suppose small h, small k. There are 2 field elements on the real line. So entire the part, Just you have to draw the one of the real line is there. So one real line is there. So initial point is H and terminal point is K. And subset of the element is the small s is there. Okay. Now we must express the order relation in between the subset of the element and the field of the element. That is called bounded. Okay. Can you understand here, students? Okay. To observe, to discuss the order exam, to any subset, to mention the order relation in between subset element and field element is there. Suppose first field element, that is the last, final element is K is there. Suppose S less than or equal to K. S less than or equal, small s less than or equal to K. Let capital S be any non-empty subset of an ordered field capital F such that small s less than or equal to K. For all small s belongs to capital S and K belongs to F. So here K be the final element. So that is the upper value is there on real line. Okay. So K be an upper bound of S. Small k be an upper bound of S is there. At the same time, initial value is a small h. That is also field element. So to observe the order relation, to mention the order relation in between subset element and field of the element, that is small s greater than or equal to h. So greater than or equal to h means that is the lower bound of this part. Small h be a lower bound of s is there. So that is the when the given the set must be, when it is the bounded. Now that must having the subset of the having lower bound and upper bound of the values, that is the field of the values involved in between the less than or equal to and greater than or equal to. So less than or greater than or equal to, that is the meaning of absoluteness. That is the absoluteness means mod representation. When it is the mod, we are getting the minimum and maximum is there. So double mod representation is also, that is the norm of this part. The maximum representation of absolute, that is called a norm. So here T varies from n into n dash is said to be the bounded if there exists a real number. What is the real number? Capital M. Capital M be any one of the real number. Now that is the boundary value. So norm T of x, here the connective mapping is capital T. So norm T of x less than or equal to, students, this is the order relation. Okay. Norm T of x less than or equal to capital M into norm of x, because M be any one of the real number. That real number is also here. Small x belongs to capital N is there. Okay. So norm Tx equal to capital M into norm of x. This is the bounded linear transformation. Here capital M is called bounded. Bounded, the bounded for T and T dash. Okay. This is called bounded linear transformation. So that transformation n into n dash is said to be continuous if it is continuous on a mapping of the metric space capital N into the metric space n dash. Okay. What is the continuous mapping? If it is continuous as a mapping of the metric space capital N into the another metric space n dash. That is the continuous of this part. That continuous discussed here. Okay. What is the continuous part? Sequence of T of xn. Sequence of here xn be any one of the sequence. That sequence is involved in normal linear space capital N. That is also a metric. Another this transformation of the sequence is denoted by T of xn. So that is also okay. Transformation of the sequence is in n dash. Normal sequence is in n. This is the domain normal linear space. This is the codomain or image of the transformation of the sequence in n dash. So the T maps T varies from n into n dash. Now here n be the sequence is xn be the sequence. So T of xn is also consisting in n dash. T of xn belongs to n dash or T of xn in n dash. Okay. All the mapping of the elements in the image of this part. So here the image is n dash. So different metric space are there. N be the one of the metric space, that is also a normal linear space. N dash should be the another normal linear space. So T maps T varies from n into n dash. So T of xn is also in n dash is there. So when what is the continuous definition? When it is the continuous, when it is the converges in T of x in n dash, T of x is also converges in n dash. What is the meaning of converges? Xn converges to X in N is there. So Xn be the sequential representation. That is the converges point is X. So Xn converges to X in N. So the domain of the elements here X be the point is there and Xn is the nth of the converges nth of the sequence. So Xn converges to X in N. Then the transformation is also applying in given this part. T of Xn converges to T of X in N dash. That is the continuous part is there. Students, listen carefully. Okay, what is the bounded part? T maps N into N dash be any one of the linear transformation when it is the bounded if there exists any one of the real number capital M such that norm T of X less than or equal to M into norm of X. For all here, X belongs to L or X in N, whatever it is. Okay. Now that is called linear transformation. That is the linear transformation function is linear mapping is bounded or linear transformation is bounded. Now at the same time that bounded from the bounded part, then it is continuous of the linear transformation. What is the continuous part? Suppose you have to take in the any one of the sequence in N is there. Then the convergence point is X is there. So Xn converges to X in domain of the part N and codomain of the part N dash. Applying the same condition, transformation with respect to the transformation, T of Xn converges to T of X. It read as T of Xn converges to T of X in N dash. Here Xn converges to X in N implies T of Xn converges to T of X in N dash. Okay, students, this is one of the most important definition for continuous part of bounded linear transformation. Okay. Students, listen carefully. This theorem is very most important in the final examination. Now, it is completely based upon the definition that is the bounded linear transformation. That is 3.4.1. Please note down this theorem is very, very, very important in the final examination. There is no doubt. Okay. Also, at the same time, we referred previous papers are also there. Number of previous papers in the university website. Okay. Do you understand? Hello? Do you understand?
Yes, sir.
Okay.
Yes, sir.
Okay. This is also one of the most important. There is no doubt. Please note down 3.4.1. Now, along with the definition, bounded linear transformation definition, and the continuous of this part, what is the continuous condition? Through the converges path, Xn converges to X in N implies T of Xn converges to T of X in N dash. Now, this theorem is also very important. So, this is our experience part. According to our experience, number of previous papers, this theorem is completely thoroughly is given in the final examination. Let T be a linear transformation of a normal linear space capital N into another normal linear space N dash. So simply enter this is the big word is there. T is simply defined T maps T from N into N dash. That is the one of the linear transformation is given. Then the following conditions are verified. Following statements are equivalent to one another. So 1 implies 2, 2 implies 3, 3 implies 4, or 4 implies 1. Okay. So first condition is T is continuous. Continuous, already we know the definition of continuous is there. Second one, T is continuous at the origin. Origin means that continuous convergence point is 0. Third condition, then there exists a real number. That is the boundedness of this part. That is also one of the definition. Here the existence of the real number is say capital M is greater than 0. So that is the M be the positive. Norm T of X less than or equal to M into norm of X. This is the boundedness part. So at the same time, the transformation is bounded. And the fourth one is, what is that? Fourth one? See this one? What is the fourth one? Capital S equal to set of X. Here, what is the X? Here, X be the normal linear space element. So here, X is also referred. What is the condition given in the set? Norm X is less than 1. This is the closed unit sphere. When the norm X less than or equal to is given, less than or equal to means then it is closed. Suppose it is less than 1, that is the open. Okay. So it is clear, that is the clear part. There is no doubt. Here given the set, that is the closed sphere, closed unit sphere set is given, that is set of X from norm X less than or equal to 1. Suppose it is X from norm X is less than 1 is there. not less than, because completely this is the boundedness of this part. So boundedness is also defined on the closed inter-unit, closed part is there. So norm x less than or equal to 1. Each and every term, each and every situation, much more important given this statement. Now, first of all, you must understood given the statement, and then we can easily prove that according to the statement, proof is also there. There is no doubt. Students, listen carefully. This is the closed unit sphere in N. Then the image of, what is the image of x? T of x. Now, image means function of x. That is the transformation of x. T of x is also bounded in N dash. Because T of x, it means that is also given the set is also image is T of s. T of s is in N dash is there. So T of s is also bounded in N dash. This is the statement, student. Now this theorem is one number of times repeated here. Don't think otherwise. Because one of the more important and finest theorem in bounded linear transformation. Because each and every theorem, you must refer each and every theorem, then automatically easily to understand entire the part of functional analysis. There is no doubt. Okay. Now here 1 implies 2. Okay, what is the one? But T is continuous is there. T is continuous. Suppose continuous, first of all, you have to take in the continuous condition, xn converges to x and T of xn converges to T of x. Okay. Now that is the condition of continuous. Now, according to the continuous condition, now it approaches to the origin. That is the second condition. So 1 implies 2. That is the first proof. In the proof is 1 implies 2. First of all, you have to take in the given the condition is T be continuous. Suppose we have to take in the any one of the sequence in N. So here xn converges to 0. That is the meaning of N is always approaches to infinitive. Now that is the convergent part. Convergent, according to the definition of convergent, limit xn, limit Sn equal to L, mod Sn minus L is less than epsilon. Here N is always approaches to infinitive. Limit N means limit Sn means limit N tends to infinitive of Sn. If the replacing Sn by Xn is there, Xn be any one of the sequence in N is there. That is the normal linear space. Suppose given the Xn is a converges to 0 because now the second condition is also now it is approached to origin. So xn converges to 0 means when it is 0, n is always approaches to infinite. Since all the given the condition by the first condition T is continuous, it follows that applying the transformation given this condition T of xn converges to T of 0. T of already we know that the 0 transformation means 0. So T of xn converges to 0 as n tends to infinitive. So by according to this one, T is continuous. This is the meaning of T is continuous at origin. So that is the simple proof. And again, T is continuous origin. First of all, we have to take in the T continuous at the origin. Then automatically T is continuous. That is the if and only if part. 2 implies 1. First of all, you have to take in the any one of the sequence in N. Xn converges to X belongs to N. And at the same time, X converts to now applying on both sides minus X is there. Xn minus X converges to X minus X means 0. What is the meaning of this one? Applying the transformation T of Xn minus X approaches to T of 0. Okay. Now T of Xn minus X. Now that is the simple property by definition of linear transformation. T of Xn minus T of X converges to 0 as n tends to infinitive. Okay. Now this is T of Xn converges to T of X as n tends to infinitive. That is the definition of, now this is the condition of T is continuous at X. By the definition of continuity condition, Xn converges to X implies T of, by the condition of 2, second condition, T of Xn goes to origin as n tends to infinitive. Now applying on both sides minus X is there. So Xn minus X converges to, that is 0. So T of Xn minus X converges to 0 means by the linearity property T of Xn minus T of X. That is, this is the simple meaning adding with on both sides plus T of X or converting into minus T of X, converting at right side. So that is also one of the part. Now conversion is also, that is the simplest method. But by algebraic part is by algebraic property, by algebraic condition applying on both sides adding with T of X. So T of xn minus T of x plus T of x. So approaches to meaning 0 plus T of x means T of x is there. So T of xn converges to T of x as n tends to infinitive. That is T is continuous at what is that? T is continuous at x. Okay, students, this is for you who don't split the classes, because without classes you can't understand the functional analysis. So don't think otherwise. In especially we are in between the class, I must explain here the number of important much more concepts in functional analysis. At the same time, thoroughly you have to practice by the subject, through the subject is there. Okay, so each and every definition is involved in theorems. Number of so many theorems are there. Okay, next one, T is continuous at origin, and we must prove that. What is the third condition? Bounded part. What is the bounded part? 2 implies 3. First of all, you have to continuous at origin is there. Now, suppose T is not bounded, because we must prove that T is bounded. But suppose we are taking the T is not bounded. That is our assumption. Means for any positive integer, a small n, or any fixed positive integer is fixed element is the xn belongs to n, such that norm T of xn is greater, because not bounded means it is greater than or equal to converse part. Norm T of xn is greater than or equal to n into norm xn is there. Okay. Now dividing on both sides by norm xn, norm T of xn by n into norm xn. Dividing on both sides, n into norm xn. In this condition, norm T of xn by n into norm xn is greater than, enter this value is 1 is there, because n into norm xn by n into norm xn, that value is 1. So again, this value is yn is there. So yn equal to xn by n into, so what is the value of y? Yn means xn by n of norm xn. So that value say y is there. So yn is there. So yn equal to xn by n into norm xn. So finally, norm T of y means yn, norm yn equals to 1 by n. Because 1 by n means, because what is the meaning of 1 by n? Limit 1 by n equals to, it is also converges to 0. Already established the limit nature. Okay. Now the function is 1 by n is there. What is the value of n? N is approaches to infinitive. Limit 1 by n equals to 0. So norm yn is also approaches to 0, because 1 by n, applying on both sides the limit nature, norm yn equal to, so that value is also converges to 0 when n is approaches to infinitive. Infinitive means 1 by 0. 1 by 0 means 0 is there. Okay, yn converges to 0 as n tends to infinitive. Finally, norm T of yn. So norm, that is the sequence. Now the sequence in n dash is there. Sequence T of yn does not convergent at the origin, because it approaches to 0 is there. Not convergent at the origin means norm T of yn is greater than 1 for every n values. Okay, so T is not bounded at the origin. Already we have to take in the T is not bounded. So we must prove that T is not continuous at the origin. So this is the contradiction part. So our hypothesis, because given the transformation is bounded. So first of all, we have to, converse part is there, and we have to derive the given the our assumption. Obviously, by the hypothesis of the contradiction of this part, given the transformation is bounded. So that simple part is there. Again, bounded is also taken, transformation of the bounded is taken, and we must prove that. What is that? Continuous at origin. That is 3 implies 2. First of all, bounded definition is there, because MB any existence of the real number. Okay, now this condition must satisfy. T is, we must show that n is continuous at the origin. First of all, you have to take in the one of the sequence in n, normal linear space n, xn be any one of the sequence. Here xn converges to 0. Okay, now here norm being a continuous function, norm xn converges to norm x. Here norm xn converges to, now there is a second condition, it approaches to 0. Norm 0 means 0. So by the inequality, first, what is the first inequality? Applying on both sides of the transformation of the part, 3.4.1.1. Okay, in this theorem, this is the 3.4.1 theorem is there. From what about the first condition? T is continuous. So regarding to the continuous condition, this is norm T of xn less than or equal to m into norm xn is there. So here, since norm xn converges to 0 as n tends to infinitive, at the same time norm T of xn converges to 0. That is the continuous at the origin part. Okay. Consequently, now that is the T of xn converges to 0 as n tends to infinitive. That is the simple meaning of T is continuous at origin is there. Okay. Next one, 3 implies 4. Okay. Now, first of all, you have to take in the boundedness of the transformation. Now, we must the closed sphere. Okay. What is the closed sphere? Now, this is the boundary condition. Here, x being the one of the closed sphere of the element is there. So, norm T of x is less than or equal to m. Okay. By the boundedness of linear transformation. So, T of s is also bounded already because here x belongs to s is there. So, entire the part is bounded. T of s is in n dash is there. So, automatically T of s is bounded. So, 4 implies 3 means according to the closed sphere region, transformation of the closed sphere, T of s is bounded. And the third one is transformation, bounded linear transformation is there. If there exists any positive real number m, okay, since that norm T of x less than or equal to m1, another real number is m1 is there. Here x belongs to, yes, that is the closed sphere element. Put x equal to 0, norm T of x less than or equal to m1 into norm x. Now that is, if it is 0, put the variable is x equal to 0, here x being the element of n is there, x belongs to s is there, that value is 0, then automatically approaches to 0. So automatically then it is the closed unit sphere, then their norm, this is the image of the a part. So T of x is in n dash. So T of x is less than or equal to m1 of x. It holds good. Okay. Now x is x not equal to 0 means another. If it is x equal to 0, theorem holds good. If x is not non-zero is there, x by norm x. This is the orthonormal part. Okay, x by norm x is in yes. So transformation is applying in the boundary region norm T of x by norm x less than or equal to m1. So again, norm of T of x less than or equal to cross multiplication m1 into m1 into norm x is there. For all non-empty, what is that? Non-zero x in n is there. So transformation is bounded. Now first 1, 2, 3 and fourth conditions are if and only if is there. 1 if and only if 2, 2 if and only if 3, 3 if and only if 4 is there. That is the simple theorem. This theorem is very most important in the final examination. Student, don't split is there. Okay. Okay. See the remark. Now this theorem, it is follows the boundedness. Then it is equivalence in the continuity of transformation capital T. So by this theorem, the above theorem is bounded. T of s is bounded. So that is norm Ty. Simply that is also norm Tx from here norm T of x is less than or equal to 1. Because that is the closed unit sphere element is say x is there. So the above part is x belongs to s is there. T of x or T of s belongs to n dash. So now when the boundary part is the norm T of x means norm T of x cannot exceed the 1. So that is less than or equal to 1. So this is the finite part. Finite part means this is the bounded part. When it is the norm T equal to, what is the meaning of norm T? Supremum of norm T of x. Simply by the above theorem, we then easily to define norm T equal to supremum of norm T of x. Here norm x is always less than or equal to 1. That is the second condition. This is the second equation of this is norm T equals to, what is the norm T value? Supremum of norm T of x, Tx simply. So here the x representation, the x of the norm is cannot exceed the 1. So because this is the finite part, so that value is less than or equal to 1. So this is the normal linear space. Capital N is a non-trivial part. So normal linear space is a non-trivial part condition is norm T equals to supremum of norm Tx. Here norm Tx means that is norm Tx means norm x less than or equal to 1. Okay. At the same time, alternative expression norm t equal to supremum of norm tx. Here norm tx equal to 1. So norm x less than or equal to 1, and another one, when the transformation of the norm will be useful, here norm t equal to supremum of norm tx. So norm tx equals to 1. So this is the third one. At the number of defined number of, now depends upon the transformation of their norm. Norm t equal to supremum of another one, norm t of x by norm x. Here x being the normal linear space element. Now x not equal to 0. When the x not equal to 0, we have to take in the norm t value is there. When the norm x, according to the boundary region, norm t equals to supremum of m. M is greater than 0. What is the m greater than 0? Norm tx less than or equal to m into norm x. So, according to this condition, you have to take in the norm of transformation is this is. Now, here alpha, beta, and y denote, alpha, beta, gamma denote the numbers of the right hand side. Okay. Now, that is the these three equations. Third equation, this is the third one, fourth one, fifth one. Okay. With respectively norm t equals to, what is the norm t value? Alpha equal to beta equal to gamma. There are so many values. We have to, then it is an equivalent to alpha, beta, gamma is there. Okay. Now, here norm tx means that is the supremum of norm tx, that is norm x equals to 1, and it is less than or equal to supremum of norm tx. Here norm x is less than or equal to 1 is there. Now, this is when it is the norm x equal to 1, that is the unit sphere. Then the unit sphere norm x from norm x equal to 1, it is a subset of the unit ball. Unit sphere can also read as unit ball is there. Here x be any one of the normal linear space element, norm x less than or equal to 1. It follows that supremum of tx. Here norm x equal to 1, and again this value less than or equal to supremum of norm tx, and norm x less than or equal to 1. Either this one, it cannot exceed this one. Okay. Now this value is an equivalent to, what is that? Alpha less than or equal to norm t. This is the another equation. And t is a linear transformation, means norm tx by norm x, and mod t into x by norm x is x by mod x is there. So beta value, supremum of norm t into x by norm x. This is the alpha region. According to the alpha value, t is a linear transformation. And the beta value supremum into norm t of x by norm x. Here x is belongs to x is less than or equal to n, and x not equal to 0. Okay. Now that is the alpha equal to beta. Both values are same is there. And at the same time, definition of t, norm t of x less than or equal to alpha, beta, gamma values is also comparing with the transformation of this part, boundedness of the transformation. Norm tx less than or equal to gamma into norm x. So beta equal to norm t of y by norm tx by norm x, and norm tx less than or equal to beta into, again this can also be written as norm tx reverse of the part less than or equal to beta into norm x. Okay. Now finally norm t equal to alpha equal to beta equal to gamma. So that value is supremum of norm tx, that is norm x less than or equal to 1. Okay. That's enough. Finally, inverse of the transformation is also inverse of the transformation applying on transformation of the part. So t into t inverse equal to t inverse t into t equals to identity. So at the same time, t inverse of t of x equal to x, because this is also a identity transfer. This is also a linear part, because this is also referred algebraic property inverse exam. T inverse of t equals to, because that is the identity. T, that is a simply read as t of x, simply read as a capital T. So t inverse t equal to identity is there. With respect to x, again that value is I into x equals to x. Okay. Now t inverse map is also a linear, because t is linear, t inverse is also a linear. That is also we have to prove the SAQ 5 is there. See this answer end of this unit, because through the above theory. Next, students, this theorem is also important. If it is not given 3.4.1, 3.4.2 is there, because continuously bounded linear transformation, these two theorems are also number of times repeated here. Okay, let n and n dash, according to this theory, just you have to see and refer. N and n dash both are linear space, normal linear space. T be a linear transformation of n onto n dash. Okay. Now, if T is 1, 1, 1 to 1 is there. 1 to 1 and T inverse is bounded. Bounded means any one of the positive real number small m such that, so that is small m into norm x less than or equal to norm t of x. So inverse of the part means now image of the element is also converting into this side. So image of the part m into norm of x less than or equal to, because T inverse is bounded. Okay. First of all, T is 1, 1, 1 to 1 and T inverse is bounded. That is also a necessary part. And we must prove that any positive real number such that m into norm x less than or equal to norm t of x. So sufficient part, norm m into norm x, okay, m into norm x less than or equal to norm tx, we must prove that t is 1 to 1 and t inverse is bounded. So that is the theorem. Okay, according to this one, first equation holds good, because when now t is 1 to 1 is there. 1 to 1 means 1, 1 and on 2 is there. At the same time, the inverse of the transformation is also bounded. So, first of all, so you have to take in any two elements given the normal linear space, x1 and x2 belongs to n, and t of x1 equal to t of x2, when if x1 equal to x2 is there, and t of x1 equal to t of x2. At the same time, t of x1 minus t of x2 equal to 0. By the linearity property, t of x1 minus x2 equal to 0. By the first condition. Now it is a real number applying here, that is the element, replacing x by x1 minus x2, m into norm x1 minus x2 less than or equal to norm t of x1 minus x2, because this value is 0 is there. So when it is the 0, norm x1 minus x2 equal to 0, because m is also dividing at the right side of this part. So norm x1 minus x2 equal to 0, here x1 equal to x2. That is the simply t is 1 to 1 is there. And again, T inverse is bounded. Here the capital T is bounded means, first of all, T is on 2. Since T is on 2, here y be any one of the element in n dash. Y be, and at the same time, there exists the element is x belongs to n. T of x equal to y, so that the relation is on 2, and T inverse of y equal to x is there. Okay. Now, from the first condition, norm applying on both sides the norm T inverse of y equals to norm y, because that is the y is also belongs to n dash. Simply that is also here m be the existing element, any real number, norm T inverse of y less than or equal to m into norm y. So this value is also, y is also belongs to n dash. So what is the capital M? That is the inverse of small m. That is 1 by m is there. Okay, here m be any one of the element. Converting into this side, 1 by m into norm y is there. Okay, here the 1 by m equals to, say that is capital M is there. So that's why T inverse is bounded. Conversely, first of all, T inverse be bounded and T is 1 to 1. And to satisfy the first condition, then arbitrary element of n y equal to T of x belongs to n dash. Now here the T inverse is bounded and n dash. There exists any positive real number capital M such that norm T inverse of y less than or equal to m into norm y. This is the condition of the last part. Okay. So norm x equal to, this value is an equivalent to norm x equals to norm T inverse of y less than or equal to m into norm y. So m of norm y means that is the mod T of x. Double mod.